Okay, I'm going to be doing 3 problems at the end of this assignment. I guess it's the 9th, 10th, and 11th problem, starting with 633, solving them for you. The number 9 problem was 633, the pulley that was accelerating. So same situation as in the previous problem, only now you have some acceleration. So the force diagram is essentially the same forces, but instead of being in balance, now they are unbalanced, okay? And it's accelerating, it's rising. So the acceleration is in this direction, okay? So that's the acceleration. So let's go back. We're going to draw a force diagram of this pulley, and we're going to try to solve for the tension in the rope based on the force diagram for that pulley and knowing the acceleration. I'm going to copy and paste that to this page right here. Okay? So let's focus on the force diagram of that point right there. We know we've got the force of the earth, the force of the chain pulling down, which is, if we assume the chain is massless, which I believe was actually in the problem, we know we've got the force of the earth on the crate in this direction, which is the mass of the crate times g. You'll notice I'm using the symbol g now instead of 10, because I want to keep everything in terms of symbols until the last step of the problem, so I can answer any questions that come up, maybe follow-up questions on an AP test that ask me, if one variable changes, how does that affect another variable? If I've already substituted numbers in before that last step, I really can't answer that question easily. So I'm going to leave it as g and know that that's going to be 10. By the way, I know my acceleration is 2.6 actually, meters per second. And finishing off this force diagram, I know I've got on the pulley 2 upward forces that are equal. And together, if I add them together, I'll make that a little bit longer. If I add them together, they're going to be longer than this one right here. Maybe I should show them significantly longer to make that point. So this is not the sum. I shouldn't do that, sorry. It's not the sum of those two. These two are congruent to each other, but together they are unbalanced with the one going down because I have an acceleration in this direction. So I'm going to call this, each one of these T for tension in the rope. One thing about massless frictionless pulleys is I know the tension is the same in all 3 sections of this rope. I'll call it T across all 3. So in the up and down direction here, my unbalanced force is in the upward direction. That's the direction of my acceleration. So my F unbalanced force equals the mass times the acceleration. And I'm going to say my unbalanced force is 2T minus M of the crate G equals the mass of the crate times the acceleration of the crate. Okay? I really know everything here but the tension in the rope. I guess I really need to go back and remember what they asked me to solve for. Assuming the masses of the chains and ropes are negligible, determine the magnitude of the force. Okay, well this is going to help us find the tension in the rope, and then we'll talk about what that force is. 2T equals mcg plus A. I did 2 math steps in one right there. I added this to both sides, and then I factored out the MC. Okay, so the tension in the rope is equal to mcg plus A over 2. So now if there's a crazy follow-up question on an exam that says if you were not on Earth, but you were on a different planet where the gravity, force acceleration due to gravity, or the magnitude of the gravitational field was not 9.8 or 10, let's say you're on the moon, how does that change the tension in the rope? You can answer that now because you can see that G is in the numerator, and if it was on the moon, for instance, that smaller number makes the tension go down because it's in the numerator. I know that's kind of off on a tangent, but that's why I wait till the last step to substitute things in, because the AP test will ask you follow-up questions like that. So 52 times 10 plus, not times 10 plus the acceleration of 2.6 over 2. So the tension in the rope is 52 times 13.6 divided by 2, or 26 times 13.6 I'm actually just, I don't have a calculator. Oh, there's one. Times 12.6. I get 327.6. Okay. Now, if you were to think about what's happening over here, the man is exerting a downward force, and his force is what's creating the tension in the rope. We've done this in class before, where you've actually had a chance to pull a rope from both ends, and you've seen the force on the rope is the same throughout the length of the rope. So whatever force you apply to the rope is the tension that's in the rope. So his pull force, F, is equal to that tension. Okay? So 327.6 newtons, let's round up to 328. That's the answer to the question. So let's go here and say 328. Submit that, and we feel good about that, I hope. I don't know why they got 320. I must have rounded something somewhere. 2.6, 52. Oh, because I used 10 and not 9.81. That's why. So they are using 9.81. Be aware of that. Hopefully that doesn't cause you problems if you use 10 and you get one wrong that really was correct. Determine the direction of the force. Obviously, he's pulling downward to be able to accelerate the object upward. The pulleys change the direction of that force. Determine the tension in the upper chain. So the tension in the upper chain and the tension in the lower chain are parts C and D. So the tension in the upper chain is pretty easy to calculate now that I know the tension in the rope, because the upper chain is this force right here. I'm drawing that pulley right there. Here's the upper chain going this way. I've got the tension going down. There's no acceleration of this pulley right here. This pulley is free to move. This pulley can accelerate upward. This pulley cannot. That pulley is rigidly fixed to the ceiling, so it's got a balanced set of forces on it. So this tension here of 320, I guess we'll use the numbers from the problem. 320 in two places going down means the tension in that chain, if I've got two tensions on the rope pulling down, going up has to be 640 newtons to keep this whole thing balanced. So you can see once you solve for the tension in the rope, these last two problems are not so bad. Okay? 650. Okay. So obviously it was 320 and change that I would have rounded up to 650 had I added them correctly with the correct 9.81 used from the very beginning. Determine the tension in the lower chain. The tension in the lower chain is accelerating, okay, with the pulley. So this lower chain here that supports that, it's accelerating up. So I've got this going down, I've got two tensions going up, and I have the acceleration. Hang on just a second. So I was starting to draw a force diagram of the pulley. I moved the upper chain over to the side there. To solve for the lower chain, the best way to do that is to think of the crate itself, the 52 kilogram crate. The upper chain is pulling it up. Gravity is pulling it down. You know there's an acceleration in this direction. Therefore, this upper chain force here, I'm sorry, that's the lower chain. This lower chain force on the 52 kilogram mass has to be greater, so I'll call it tension of the lower chain, has to be a longer vector than the force of the earth on the crate, on a block. Okay? This is 520 newtons if I use 10. So T minus 520 is going to be equal to 52 times that 2.6. That's the acceleration. So this is ma. This is the unbalanced force right here. Solve for the tension in that chain, and you're going to get the same 650 that we had before, I believe. Yeah, 655.2, that's using 10, so the actual number using 9.81 would be a little bit less. So the tension in the lower chain is 650. Okay. All right, hopefully that made sense to you. Now I'm going to do the next problem on a different screencast.